Good afternoon and welcome to MAE 113, Calculus for the Liberal Arts. My name is Richard Kohar, and this is our first tutorial in algebraic skills and limits. Of course, make sure everyone say that you can hear me okay in the chat. So the question is, can you stop putting emphasis on misleading or trick questions, instead what you have taught and explained to us? The emphasis is on the homework. That's the answer to that one. So the questions were from the homework that we had done previously. Excellent. Thank you for saying that you can hear me okay. Okay. And if is there any other questions? Perfect. Okay, so what this is about today is about algebraic skills and limits. I think that there wasn't enough practice on the homeworks for what I was kind of expecting you to be able to do on the test. So this is where we'll take a pause, and we also get to go over some of the stuff that I've already taught previously. So the first thing is, because again, I kept having questions sent by email asking me about limits and if they were defined or if they weren't defined. So I think that's a good time that we can actually answer that. So let's just kind of recall a couple things that I've taught previously. We said that polynomials are continuous over the reals. So what is a polynomial? Well, here's an example of a polynomial right here. So I have like x squared plus 2x minus 3. And we also remember what the point of continuity is. So we said that a function is continuous at a point at x naught if the limit of that function actually equals that value. So that's something that we had seen previously. So that means that if I pick, say, x equals 5, and since f of x is continuous, or it's polynomial, which means that it's continuous over all the reals, that actually means that I can use that definition. So that actually means using this, I have my function here. I'm going to let that x go to 5, which means that it should be evaluated at that function at 5. So I can just substitute those values in, because again, it's continuous. So then I get 5 squared plus 2 times 5 minus 3 all over 25 plus 10 minus 3. So that's 35 minus 3, which gives me 32. Is everyone okay with what I've done there so far? So like it's a continuous function. And the same thing is, we could also apply those same rules that we had previously learned. For example, again, we could apply those same rules apply still. you know, using our sum rule. So same idea. So again, 5 squared plus 2 times 5 minus 3, again, still gives me 32. So again, those are just using the limit rules that we had used before. Sorry, someone wrote yes. Someone's okay. Is there a question, or I'll just pause for a second. No, I'm just waiting. Oh, no, you were asking if we were okay with the question. Okay, yes, good. So everyone's okay with that. Okay, so then the second part, we had seen where the polynomials were continuous over the reals. Then we have rational functions are continuous on their domain. And what are rational functions? That usually means that it's like some sort of function where I have kind of a polynomial over another polynomial. So these are polynomials. And from our previous lectures, we had seen that they're continuous on their domain, meaning that their domain is defined where q is not equal to 0. So now this is kind of going back to, I'm not like, it depends on which provinces that you came from, but here's an example. So either the 10th or 11th grade, depends on where, we had something like this. And these are called rational functions. So we'll have a function like this. And what this says is, first of all, one of the questions would be like, what is the domain? That's a question that could be easily asked. What's the domain of this? And the domain is for wherever this makes sense. This is defined. So that means that this bottom here cannot equal 0. So we have x minus 4 cannot equal 0, which means that x cannot equal 4. So it then is, based on what we have up here, that it is continuous on the domain minus infinity to 4 union 4 comma to infinity. So that's the domain that we're using. And then the next thing is, you would ask, okay, how do I draw this graph? And it might be a little bit tricky for this. This kind of looks weird to draw out. But what we would do first is we would simplify it. So we would use x squared minus 16 over x minus 4. Now we can simplify this by using our difference of squares. And so I'm left with x plus 4. Now again, the original function, I still need to apply the same domain to this. So this is going to be our function. It's actually just, if we simplify it, it just reduces to x plus 4, but it's still on that domain from minus infinity to 4, and from 4 to infinity. So it's not defined on that, which means if I can actually draw this out, well, I am going to draw this out. So if I draw this out, so here's my x, my y axis. And let's see, I start out 4 here, I have 4, and I have 8. Because if I put in 4 there, that would be the... So it's going to start at 4, that's my y-intercept, and it's going to go up the same point there, the same slope of 1. And I skip that point right here. So this is... So I've drawn really x plus 4, but because of the original function and the domain was not defined at 4, it has a hole. And what we can actually say then is, based on this, from our previous discussions, that x equals 4 is a removable discontinuity. Okay. So somebody might say to me, they might go, is this a trick question? The limit as x goes to 4 of x squared minus 16 all over x to the 4. So again, they would say, oh, it's a trick question because if I put 4 in here, I got 4 minus 4, that's 0 over 0, or I have an undefined function, which then means that I can't solve it. But if we go back to the original, if we look at the graph and we look at our limits, as we're looking from the left-hand side, it's going to 8. And as we look from the right-hand side, it's going to 8. So we know that the limit exists because the behavior in the neighborhood of x equals 4 is the same. So again, we know that the limit going to 4 from the left-hand side is equal to the limit on the right-hand side. And so this implies that the limit x equals 4, as x goes to 4 of the function has to exist. So that's just based on our graph. Okay. So if you just had this, and so it was on a question like this on a test or something like that, can we solve it? And the answer is yes. It does exist, even though how it's written currently, if I just put in 4 in there, that would give me 0. So what do? We do very similar to how we did it in high school. We reduce and we simplify. So using my difference of squares again, and so actually I can just rewrite what I had currently on the first page. And so I'm simplifying that down. And at that point, I don't have any issues with the fraction being 0 in the denominator. I don't have to worry about that. I can actually just substitute now in. So if you really wanted to be using your rules at this point, sure, you could do it this way. So 4 plus 4 equals 8. So going back to the questions, there was questions like this in the homework. However, I think we just need more practice. So this was from the assignment. I can't remember which assignment it was. I think maybe the second one. And this is from section 1.2 on limits. And this was question 13. And so they had this one, which was that the limit as u goes to root 3. I have u minus root 3 over u squared minus 3. Then, again, remembering my limits, so again, you might say, is this defined? Well, if you just substituted that in, you have root 3 squared, which gives me 3. Then 3 minus 3, that's 0. So as it sits currently, you might think that it's not defined. But with a little bit of manipulation or a little bit of simplification, we can actually reduce this. And we have this, which means I could use my difference of squares. Now I know that 3 is not a square as it is, but we just take the square root of it. So you can do u minus the square root of 3 and u plus the square root of 3. Okay, that's fine. So that cancels, and I'm left with root 3, u plus root 3. So then I have 1 over, I can actually substitute that in now. I don't have any issues of it being 0. So I have root 3 plus root 3, or 1 over 2 root 3. Oh, sorry, I didn't look up. Could we skip that third last step? Okay, and this goes for Ms. Tran. Which, did you mean this one right here? Yes. I mean, that's fine. You don't have to show that step. Yeah, I'm fine with you don't have to show that step. But I'm just trying to show for other people who have an issue with limits not existing, I'm just trying to use some of the rules that we've had previously. Okay, perfect. So we had that one. What other ones did we have on the homework? Well, we had also 45. They like to use u in this. So I have the limit as u goes to 0 of u cubed plus 2u squared plus u all over u. So again, everyone would be freaking out that, oh no, it's not defined because I have 0 in the denominator. But again, with a little bit of simplification, you know, that this is defined on it is continuous on its domain, and we just need to figure out what, we just need to simplify this a little bit better. So, in the chat, somebody say what I should do to somewhat simplify this, or what's my first step that I could do to try to eliminate that u in the denominator. There's always just a little bit of a delay, so I'll just see if other people factor out a u. Exactly, yes. Perfect. So to do that, yeah, pull out the u. Now notice how I'm very careful about that. I see some people start canceling out u's and doing some weird canceling. like things that they shouldn't be doing. So I'm going to show the step of first we're going to actually factor out that u first. So I have a u times u squared plus 2u plus 1 all over u. And I have a u times this term, and I can actually cancel it at this point. That's fine. But I see people do something like this, and this is not allowed. What's not allowed is if I had something like a plus b over a. Now I have an addition here. I see people do this, and you can't do that. You can't do that. You can only do this if it's multiplication. So then I can cancel it. So if I saw somebody going like, oh, I see u here and a u here, and I'll just cancel it. Like this. You can't do that. Could you use the factor pyramid instead? Would that work as well? The factor pyramid. I'm not quite sure about the factor pyramid unless you're talking about Pascal's triangle, and that's what we're using to expand a binomial. I think that's what he means. We use that for when we're expanding something like a plus b to the like 3. And we use those numbers. Okay, yes. That's when we are expanding something. So we have something like a cubed plus a squared plus a plus nothing. And then over here would be b3, b2, b1, nothing there. And so these would be my coefficients. 1, 3, 3, 1. Yep. So can't do that. You have to, again, I can only kind of cancel out if it's a multiplication, not if there's an addition. So I saw lots of that. Okay, what next? So we've done that. And now there's no issues. I can actually substitute it in here. So I have 0 squared plus 2 times 0 plus 1 equals 1. Okay, what else? What other weird... Let's do... So here's a limit. We'll do x goes to 9. Oh, okay. Since we're going over homework questions, could we go over one average cost function question in the while the test question is still fresh in my mind? Of course we can. Yes. But I will do that right after this limit question. We'll take a little pause and we can go do that. Okay, so I have x minus 9 over the square root of x minus 3. And, okay, everyone will start panicking. They'll go, oh no, there's 9. I can't substitute in this 9 yet, right? Because I have square root of 9 is 3, 3 minus 3, 3 minus 3 is 0. And again, I could put a 9 over top here, but that is still not, I still have something that is indeterminate. So I have 0 over 0 still. So what I can do is, instead of rationalizing what we've done usually before with rationalizing the numerator, we can actually rationalize the denominator. So rationalizing it, I'm going to take the radical conjugate. So if I do that, I have x minus 9 in the top here, square root of x plus 3 all over. Now in the denominator I have square root of x times square root of x, which is x. Then I have a plus 3 square root x, and then a minus 3 square root of x, and then I have a minus 9. So these cancel, so I'm left with x minus 9 all over square root of x plus 3. And then I have x minus 9, which is nice because now I have very similar. I have this term times this term, so I can actually cancel that out. And I'm left with the square root of x plus 3. So again, square root of 9 plus 3, 3 plus 3 is 6. Okay, so could we go over 1? Yes, of course. And if I pull that up out of the, just give me a second while I pull up the assignment. So I'll call this a detour, because this isn't about the limits. We're talking about an average cost function. And so we'll pull out the big binder of notes. Oops. There we go. So we had talked about average cost functions before. So this is what we had covered in class. So the average cost is just taking the cost and dividing by x. And then if I wanted the marginal cost, or the marginal average cost, then I would take this function and I would take the derivative of that. So we have c bar is equal to the cost function divided by x. So again, that kind of gives you the cost of each unit. So for instance, like I have a cost, I made, I pressed 1,000 vinyl, and it cost me, let's say, if it cost took me and I had $1,500, let's say $15,000, and I had pressed, I don't know, something like 250 vinyl, you know, roughly that works out to about $60 per album that I pressed. So that's like my average cost. So that's what the average cost function is. Kind of gives you that per unit cost. And then if I want the marginal, and again, I've said that throughout our lectures when we're talking about it, that if I wanted the marginal, that's code word for derivative. So this basically means the marginal average cost is the derivative of that. So in the homework, we had question 1, and the cost function that we were given was 5,000 plus 2x. So then to find the average cost function, divide by x. So that equals 5,000 for x plus 2x over x. Now I can actually cancel this because, again, there's the multiplication, so that cancels. So I'm left with 5,000 over x plus 2. And so that's part A. And part B that they're asking is find the marginal average cost function. So again, before I do that, I would write this. Like that. So if I take that derivative, the derivative of that, so the -1 comes down in front, so I have 5,000 minus 1 times x to the minus 2. This is a constant, so that's 0. So I have minus 5,000 over x squared. Someone said, but earlier you had an example where you couldn't do algebra like this. I don't recall where I have that. I can say that the numbers aren't so nice sometimes. So for instance, switching over to kind of our, going to my screen, there's one over here, for instance. Like this one's not super nice. But, I mean, we can still look at something like that. So if I looked at something like 2, and switching over here, for factoring out the denominator on each numerator individually. Okay, I can't quite follow what the question is. For factoring out the denominator on each numerator individually. Okay. I'm not sure. We'll have to, if you send me an email with maybe the example that you're thinking of, or if you want to type it in the chat, just give me the example and we can see if we can figure that out. But sometimes I think they mean that, oh, okay. Okay, so sometimes there is cases where, yes, of course, where we can actually do it. And okay. Okay, so good. You guys are just following along with what I had written out for my tutorial. yeah, we can. We're going to get to the part where I can't do anything with it, and there are times when you can't do anything with it. But if you had, sorry, I was just looking at two. The only thing that kind of gets gross about stuff like this here is kind of these decimal places, and there's kind of this fine line of trying to show you real world kind of functions, but at the same time not trying to bog it down so much that you're getting hung up on the numbers. But again, it's the concepts that were kind of interesting to teach. But you know, there's that classical debate of teaching to the test or trying to teach for the real world. And so we're always trying to walk that fine line. So again, you know, this would be a little bit trickier where I have this derivative to take care of. But I have 2 times 3 gives me 6, x squared minus, and then I have 0.0. And so I have 0.03 times 2 gives me 0.6. It's 400. So that's kind of like taking, again, that's taking the derivative of the cost function. Okay, so I think they mean, okay, yes. So we'll get to that. Is there times where the function doesn't exist? Yes. Yes. There are times when there's nothing that you can do to fix it. Okay. So here was, I'm not sure if this was the question from the textbook or not. I have 47 written down. Yeah, I'll put it down. Okay, so in this case, here's something that I can't do anything. I can't factor, I can't do anything. I don't have any forms or things to cancel out. So I can't simplify it any further than this. So I cannot simplify or factor. Okay, so we're stuck. Now, why are we stuck? So let's go back. In this case, I had this function, I could simplify it, and I got a whole. So it depends on the type of discontinuity that we have. So if we have something that's a removable discontinuity, I should be able to find out what that limit is around that point, around that discontinuity. But where do the limits not exist? We know, we can think of one, and for instance, we've looked at this before where we had this function is 1 over x. And if I look at that limit as x goes to 0 of 1 over x, if I look from the left-hand side, it's going off to, and I know I'm writing equals, and I know that is, but it's going off to negative infinity. It's not defined. And then on the right-hand side, it's screaming off to positive infinity. So again, we have a mismatch of the values. It's not, that limit doesn't exist. And you see what that form is like. It's like 1 over x. And it's very similar to this as well. I have this 1 over kind of x idea. And let's see. what I can do is show you a graph. So again, we'll use Google. And I will switch over to the screen. We'll use Google here. And we're looking at 2x over x minus 2 squared. So just to have a look at the graph. So again, the original question that we were working at here was that the limit as x goes to 2. And so what's happening around 2? The limit is going off to infinity. So again, I've got kind of an infinite discontinuity that's happening around 2. Now both sides are going to infinity. So do we just check if the left side equals the right side limit then? It depends on what you're looking for. So let me just go back to my sheet of paper. So someone was asking is, do we just check? Again, that shows that the limit exists. So that exists, and if they do not equal, then the limit does not exist. That's correct. Yep. Now, again, let's be very careful. These have to equal a real number. It has to be a real number. So these have to actually equal some number. It has to equal a real number. And by that, I mean, while we know what the kind of behavior is looking like around on the left-hand side of this x equals 2, it's going off to infinity. And on the right-hand side, it's going off to infinity. It's not a number. It's going off to infinity. And so when you have one of those going off to infinity things, it's not, we don't actually have a limit then. Oops. There we go. So again, if it is left or from the right-hand side, then it doesn't exist. So again, it has to be a number. So infinity is not a number. Okay? And let's see. So you'll kind of run into problems like that when you kind of have 1 over x. I mean, let's have a look. So again, there's from the left-hand side, it's going to negative infinity, and from the right-hand side, it's going to positive infinity. And you can also keep an eye on what that looks like. So I can actually shift this. So in this case, I've done 1 over x plus 1, and so it's shifted to the left by 1. And so now I have that discontinuity is moving. And same thing is, I can also move that over. I can make that both go to the same, to positive infinity. So things like that I would keep an eye out for. That's when they don't exist. That's when we have an infinite discontinuity. Okay. Is everyone okay with what I've done so far? We can just do a little bit more practice then. This one does have a limit. Now, again, usually questions, when I ask for them, I usually say, if there's something like this, which is, find the limit as x goes to 2 of 1 over x minus 1/2 over x minus 2. I usually will say, find that limit, and I do expect a value. If I am looking for something where the limit doesn't exist, for example, using like this, I wouldn't just say, find this limit. Oh, that's a good question. Someone wrote, so effectively any 1 over x, any number is equal to d and e. You got to be careful about that. I'll be right. That's a good question. I think we should look at that. But I'm just asking in terms of what to expect from me on a test. If somebody said, like, this isn't, I wouldn't just say, like, find me that limit. What I would usually say is something like, show that the limit as x goes to 0 of 1 over x does not exist. And when I see something like that, expect a kind of ones, going from the left-hand side and from the right-hand side type of argument, showing that there's, it's not the same around the same behavior around that point. Okay, so you have to be very careful. We'll get back to that one. So that question is, here we go. Yeah, and it starts to do some, like, you'll see it kind of go up and down, depending. If it's even, it'll go up, all of it will go up, and if it's odd, then it will flip. I can go back to the screen. So here it is. It's both of them. So when it's even, it's both up, and then when I have it to cubed, I have it down. So it's kind of, one goes down, one goes up. And now when I go up to the fourth, you'll see that both will go back up. It's that squaring effect, right? When you take a square of something, it's always going to be positive. So again, that's why we have it both going up. Now, Mr. Walker has asked, the limit does not exist. The limit doesn't exist at that point, x plus 1. Okay, so that would be minus 1. So the limit doesn't exist at x equals minus 1. So let's actually sketch that out. Switching it back to this. So I have my axes, and I'm going to draw here's my x minus 1. Whoop. Something like that. Here's my vertical asymptote. And this is all good stuff because eventually we're going to be sketching some more functions later using, they call it curve sketching, and we use all that information that we have from calculus to kind of figure out what the graph looks like without using a computer. So this is a function I have 1 over x plus 1 all to the 4th. And so that limit as x goes to minus 1 does not exist. And why I was saying just be careful is because, you know, the limit everywhere else exists. So for instance, I could go x goes to 0 of 1 over x plus 1 to the fourth. This doesn't cause it to go to, doesn't cause the denominator to be 0, so I can actually just substitute in my value here. So I have 0 plus 1 to the fourth. 1 to the fourth is still just 1 over 1, or 1. So yeah, just be careful of that in terms of this, that in this case, the limit does not exist at x equals -1 because of an infinite discontinuity. Good questions. I like that. So what you should do is we should take 2 minutes and do that. And I actually mean like grab a piece of paper and a pencil and scribble it out. And again, thinking of how you can simplify that. And then once you get what your final value is, put it in the chat. Let's see what people are getting. Okay, so I have 1 over 4. I wonder if Mr. MAE will chime in on this. What other? I have 1/4. Anyone else? Someone wrote 1. Okay. Let's see. This is what I'm getting 0, so I'm probably... Yeah, again, it's all these things that we had learned previously in 103. So the thing that we have here is that's okay. That's why we're here for the tutorial. Sometimes algebraic skills are a little rusty. That's why we're having a tutorial on it. And I'm just... Let's see. The way that I would do it first... Okay, so we all see that the issue that we're having is that we have 2. So I have 2 minus 2. That gives me 0. So, okay. So that means that we need to do some simplification first. So what I'm going to actually do is I'm going to write this. This is the numerator. So I'm going to have that over here. I'm actually going to split this up. So everyone is okay with me. I have like... plus b over c. And everyone's okay if I wrote 1 over c times a plus b. So everyone's okay with that? So if I had something like, I don't know, 4 plus 5 over 6, I could write that as 1/6 of 4 plus 5. Yes, okay, good. I should finish this off. So I have 9/6, and there it is, 9/6. So that's what I'm going to do here. I am going to just write my denominator here. So I have 1 over x minus 2 times 1 over x minus 1/2 okay. And everyone's like, what are you doing? That does not look nice. Stop it. Sure, but what I'm going to do now is I'm going to distribute that. So I'll get 1 over x times x minus 2 minus 1 over 2 times x minus 2. And I want that limit applying to all of this, so that's why I have the brackets around it. Okay. So now what I'm going to do is I'm going to find a common denominator, meaning that this has to match this one. I have x times x minus 2, and I have an x minus 2 on both of these, so that's good. So I won't do anything with that, but I have a 2 over here. So again, I'm going to multiply essentially by 1, so it's 2 over 2. So I'm going to put 2, and up here I'm going to make it 2. So I match that. So I have this over here, and I have this one over here. And over on this side, I'm missing an x. I don't have an x here. So I'm going to multiply essentially by 1. So I have an x on the bottom and on the top. Okay. That looks good. So because I have a common denominator, I can write this numerator up top here the same. So I got 2 minus x, and I have 2x times x minus 2. Okay, I still can't simplify anything. Oh, but we do. And the reason for that is I have some term up here. I have 2 minus x, and I have an x minus 2. So again, what we're going to do now is factor out a minus. So I have that negative x. That becomes positive now. And that 2, that's the positive 2, becomes a minus 2. This cancels. Right? I'm allowed to do that because I'm multiplying everything, so I can cancel that. And I'm left with 1 over 2x. Now I have a minus. Hopefully, no one is upset that I've done anything like that, because that's where I'm getting that negative. And now I can substitute in that value. I have a minus 1 over 2 times 2, or I'm getting 1 over 4. So negative 1/4. Yep, negatives. That's why it's always good to have people watching you when you're doing it. It's good. I like doing it during class. People are watching it. Dropping a negative, adding a negative, yeah. It's a common mistake. Why are we so careful about negatives here? Again, this is a good teaching moment. You know, because we've done more calculus now, when we're going through this the first time, you know, paying so much particular attention to details like negatives or something. Again, you're paying so much attention trying to learn a concept. But, you know, for instance, when we're doing a negative, why? They're important. Because if we're doing something like with calculus, and we were looking at, say, the first derivative, or we're looking at the second derivative, you know, if one is negative and it should have been positive, we're going to get the wrong interpretation. So if this was positive and it should have been actually negative, you will start to misinterpret something. Like you might think that you found a maximum, but really you found a minimum, and vice versa. How would we know when to do this strategy over another? When do we use? Well, that's my way was faster, but without showing there. You know, again, like that's what I paused for Mr. Maple. You know, there's lots of different ways to write something, and there's different ways, and that's why I was already thinking. I thought this was the nicest way to show it, possibly, but again, there's lots of different ways. As to Mr. Frampton's question, when do we practice? Practice and experience. I know that's not a very satisfying answer. But I would say when you see something like this with a fraction, like this, start to think, okay, I need to find a common denominator. When you see something like that and you need to do some simplification, again, you're going to have to find a common denominator. So I would say when you see a fraction, something like that. I hope that answers the question. So again, like, I see fractions. think common denominator. Same thing with like the, what were we using? We were using the square roots. When we're using square roots, start thinking radical conjugate. We're going to rationalize a numerator or a denominator. Oh, okay. Perfect. It's good that you catch. And then, well, I was nowhere to be found. NGL. I wouldn't have caught it this time. Okay. NGL. No good luck? I don't know. I'm terrible when it comes to abbreviations. So, what else do we have? Oh, not gonna lie. Okay. Yep. So we did that one. So what we should do is, I'm not going to lie. Okay, perfect. It's always good when we're all learning. Yeah. I remember IMHO, in my humble opinion. So let's go to. We had to do something like prove. So prove that it's equal to 0. And same thing again here. Somebody was asking me again about this. And there's, again, we had the test. We did the solution. And now that we've got the limits, again, fresh in our mind, let's try this. And using our definition of the derivative, again, uses that limit. And why are we using all those techniques for those limits? And it's because to do stuff with first principles, or by the definition of the derivative, it has a limit. And we have that tricky denominator, which is going to 0. So again, we have to simplify it. We're simplifying it and then applying our limit laws, or allowing the delta x go to 0, but we can't actually do it yet. So this is C. C is our constant. And again, it doesn't matter what is going into this box. It could be anything. It could be 3, it could be 4, it could be 5, it could be anything. But whatever is coming out of it is just C. And you could put that as equal to 7. And I think that's a good tip. Maybe we'll do that, a little bit of a concrete example. So let f at x equal 7. Okay. And then I'm going to have that derivative limit, or that definition of the derivative here. Okay. So what does this mean then for x plus delta x? That function, it's still 7. So this is going to look really basic compared to what we've been doing previously with all of our algebraic manipulations. But here we go. I'm going to substitute my value for f at x plus delta x. So that's 7, right? And same thing over here. I have minus f at x, which is 7. So I have minus 7 over delta x. Now I have 7 minus 7, that's 0 over delta x. I have 0 divided by something. And again, 0 over anything, 4, that's still equal to 0. 0 over 7, that's still equal to 0. So this whole thing, that's 0. There's no delta x's in this at all. So I don't have to worry about it. I can actually let that limit, and there's nothing for me to apply, so it's just 0. Now, again, when we're doing a proof, we want it to hold for any number. So this is a very common thing that we do in math. If we're working on something that's quite abstract, we'll come up with a concrete problem. And then, hopefully, we can abstract. And by abstract, I mean we'll kind of let it be not just 7, but maybe 8, 9. This is where we start. We just kind of replace what 7 instead with a letter. So instead of 7, I'll use C. I have C here. Same thing over here. So we just kind of white this out. We have 7 over here. We've replaced it with C. So I have C minus C. And C minus C is still 0. And then if I have 0 over delta x, that's still 0. And that gives me that equal to 0. Is that okay? I think somebody had emailed me, and hopefully that answered the question there. And if you're okay with saying like, yep, that's good, or you don't want to acknowledge it in the chat, that's okay. But hopefully that answered the question about that. Yes. Okay, perfect. Okay, excellent. What are we going to do? Because again, the limits are important because we're using it so much, and it's kind of underpinning the derivatives, and it also underpins the idea of integrals as well. So here's something like this. I have a function, f at x is 1 over x squared. Find f prime using the definition. Of the derivative So your first step again should be writing out your definition, which should be automatic at this point. So I have that function. And if I substitute in this x plus delta x. This is 1 over x plus delta x squared. So at this point, I can actually substitute in that value. Okay. So again, when I see a fraction like that, immediately, when am I going? I'll probably use a common factor. I'll probably use a common denominator, but I am going to use that. I am going to rewrite it just a little bit neater. And by neater, I mean I'm just going to write that 1 over delta x out in front here, because that's just my denominator, and just to give me some more room. So yeah, I am going to do a common factor. So again, I don't have an x squared on this side, so it's going to be x squared over here. And I don't have a x plus delta x squared over on this side, so everyone's okay with that. You know, essentially right here, I have x squared divided by x squared, and again, I could cancel that out because that's 1. I'm just multiplying essentially by 1. And while I was blabbering, what I was trying to write was x plus delta x squared. And then I also need it up top here. I can write this over the same, the same fraction now. Okay. So again, people don't start canceling out that over that. I can't do that yet. What I need to do, I need to still simplify this just a touch. And to do that, I am going to expand that. Now, over here, what I'll show is x plus delta x squared. So again, just expanding it out. So I'm going to expand that, and again, it's inside of these brackets. So x squared plus 2x delta x plus delta x squared. distribute that negative. So I have the negative x squared minus the 2x plus delta x minus the delta x squared. So I have that cancels. That's it. That's all I have. So I'm left with the minus 2x delta x minus x squared. So I'm going to factor that out. So I'm left with the minus 2x. The delta x is coming out in front, minus delta x. This is where I can cancel. So I have delta x times this, and this is again x squared times this term over here. So they're just multiplications. I have this term and this term being multiplied. So, and it's being multiplied by 1 over delta x. So here I can cancel. I can actually cancel this part right here. So that's good. Okay, now what have I got? I've simplified it, and if I put in a 0 here, it doesn't cause me any issues. It doesn't cause me any issues at all. So what I'm left with is minus 2x minus 0 over, I have x squared times x plus 0, or x squared, and I'm left with 2x over x to the 4th. Okay, so part of this, what we should do is we should do a check. Because we got more information, we got more knowledge, we can do a check quickly. So we have our original function was 1 over x squared. And that is equal to, writing it as x minus 2. So that is what we have, x minus 2. And then using our power rule, that minus 2 comes down. Minus 2 minus 1. So I got minus 2 times x to the minus 3. So I got minus 2 over x to the 3. Yes. Good. So again, it goes back to Maria's question, which is, do we need to simplify? Well, we've done it 2 different ways, and I want to check my answer, and I'm almost done. So I could factor out. So I'm left with the minus 2 over x cubed. Good. Is everyone okay with that? There are some people who can do it in fewer steps. If you're comfortable enough to do it in fewer steps, fine. But until you're pretty good at it where you can write it in pen and you're not covering it in whiteout, which I didn't do too bad. I wasn't paying attention here. Write out your steps. And again, it's practice. Let's see, one more. What else can we do? Let's do this limit here. So I have x cubed minus 8. So we've been doing a lot of difference of squares, but we also can do difference of cubes. So we can do 3 cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So that's our difference of cubes. And we actually see here that this is a difference of cubes as well, because I can rewrite this 8 as 2 to the 3. So again, using my difference of cubes, I have x minus 2 times x squared plus 2x plus 4 I also need to factor the trinomial down here. So I have man, and it's just to remember, multiply, add, and the numbers. So I have to make sure that they multiply to give me 2, they add to give me minus 3, and so the two numbers I can think of is minus 2 and minus 1. So again, minus 2 minus 1 gives me minus 3, and multiplying negative 2 and negative 1 gives me 2. So and that's nice because I can cancel out these x minus 2 and the x minus 2. Oh yeah, and why am I doing this? Because if I put the 2 in here, the 2 squared, so that's 4 minus 3, that's 6 plus 2, that gives me 0. So we need to do some simplification. So actually I'm almost done at this point. Because now if I substitute in that value, I have 2 minus 1, that's still 1. So then I have 2 squared plus 2 times 2 plus 4 all over 2 minus 1. Gives me 4 plus 4 plus 4. 3 fours is 12. So probably just as a little recap, you know, if I had approaches, maybe called that. And I have this function here. And I have to do my derivative using first principles or the definition. What would I be doing? Radical conjugate. Because I need to be able to handle this square root. If I saw something like this, 1 over x plus 2 can even do it squared. I see something like this, a fraction, I would be looking for a common denominator. So then the real question is, what do I do with that? And that is the end of our tutorial session. So that's what I would like you to try at home. And try that at home, finding the definition, using the definition of the derivative, find the derivative of 1 over the square root of x. And when you have it, and when you think you have it, send me an email, take a picture of it and send it to me. And I'll check it, I'll look at it, and we'll see if you've mastered the algebraic skills that are required for this. Like I said, probably one of the worst things to do is making the same mistake again. Because you knew, at least for me, because I know that I watch for negatives or something like that, and no, I'm going to, somebody had written about the test. I had made a comment on the Moodle. Again, I don't like talking about it publicly, about marks, stuff like that, but what I'm going to do is basically, I'm reducing it out of 50 down to 46. 44. So the test is out of 44. So whatever you got in the numerator, it's now, the denominator is 44. Okay. So I'm not going to, okay, perfect. And of course, if you're going to check this, this is equivalent to x to the minus 1/2. If I take the derivative of that, that negative 1/2 comes down in front. I have x to the minus 1/2 minus 1, or that's equal to 1/2 x to the minus 3/2, or minus 1 over 2 square root of x cubed. And that's what you should expect to see. So again, here's 1, 2, 3. So if you want to do it, again, write that out. Now that you've had some practice at this, do it fresh in your mind, and then you can always take a picture. Send me a nice PDF so I can read it easily, and then I will make some, if you need me, if I see anything that's out of the ordinary, I can make comments on it. Okay, thanks everyone for tuning in for this tutorial, and I hope you have a great night. Take care.